Hello everyone, I hope I am clearly audible. So let's start with today's class. So this is lecture number 7, and in the earlier classes we had covered the introduction to the course. Then there were different approaches in order to represent the system, that is basically to generate the models for the system. So for that we looked upon this first order dynamical systems, second order and higher order dynamical systems. So this usually gives us process transfer functions, that you can also call it as process models. So using this transfer function we can analyze the stability of the system, and once we analyze the stability of system, so the whole purpose of analyzing the stability of the system is basically to check whether the implemented controller is able to control the desired process in the manner that we want to do. So for that we just introduced about feedback control, feed forward control. Then we looked upon stability analysis, whereby we looked upon different approaches such as direct substitution, frequency response method, and in that we looked upon body stability criteria, Ruth array. So all those things we studied in this stability analysis. Then in the last class we looked upon this design of feedback control systems, whereby we looked at what all steps are to be followed in order to design any control systems. So that includes defining the synthesis problem, then selection problem, which involves selection of the controller. Then the main part was related to the tuning of the controller parameters. So ultimately from the first 6 chapters we studied that how can we design a PID controller system. So given any process, how can we use this PID controller in order to control the process, and majority of the part was related to this process modeling, stability analysis, and then design of the controller, that is basically tuning of the controller parameters. So and now in the next 2 sessions, that is this session and the next session, we will be looking on to this advanced control topics, that is apart from PID controller, what all kind of controllers can we use, or apart from the conventional PID controllers, what all enhancements in this PID controllers can be used for using a better controllability of the system. And then in the next class we will just take a brief look on this multivariate and batch process control, and again I will give a summary of all the lectures week 1 to week 8 in the next class. So we'll be going through the basic concept of each of this in the next class. So you can join next class if you want to just get a brief overview of the entire course. That can help you revise the syllabus very well. So yes, in today's class we are studying advanced control topics. So in that the subtopics that we are going to study is related to cascade control, then split range control, override control, then auctioneering ratio and inferential control. So all this don't require the process models, in the sense they don't need the knowledge of this process. Basically what all things that are happening in the process, we are not concerned with that. We only need that how my manipulator input will affect the measured output. So we only need these 2 inputs, measured manipulator input and measured output, and on the basis of that we can generate our control strategies. Whereas in the last 2, so these 2 we call it as model based. So what we propose is we can have an idea about the process model, that is if we are using a CSTR, then we can just have the governing equations of the CSTR that can basically include the material and energy balances. So that can give us a model. So how we can use this model along with the conventional control approaches in order to get a better controllability of the systems. So we will be using the model in order to control the system. So in that we have this open loop control and internal model control, and then a fairly advanced techniques, that is model predictive control and dynamic matrix control. So these are the contents of today's class. In the last class, we had just started with few of the controller tuning approaches, such as, let me just share that screen also. So yes, in the last class we were looking onto not this one, where is the index? This slide. So in the last class we were looking on the synthesis problem, selection problem, criteria based controller tuning. So basically we looked onto this 4 tuning method, but we had not solved numericals related to that. So in this class, let's just start let's say around 2 to 3 numericals related to these topics, and then we can start with the theory behind the next advanced control topics. So let's just start with the numericals. So over here, this is the first question that we are solving today. So the question states that for the given block diagram, we have to use Ziegler-Nichols rule and determine the value of Kc and tau I for this system. So over here you can see that this is our controller. This is the process model, and this is our, you can say, lag. So for the given process system, we have to determine the controller parameters, that is Kc and tau I, using Zn rules. So basically you need to find this ultimate gain and time period, and then you can use the table related to Zn tuning, and using the correlations in that you can find the controller parameters. So I'll just share the table with you also. So over here you can see that we are having a closed loop system. So the table that we will be using is basically the parameters related to the closed loop tuning. I think so that is provided by this table. So basically using the block diagram and using this table, you have to find the controller parameters Kc and tau I. And for doing that you have to use that table, and in that table you just need to calculate 2 parameters, that is the ultimate gain Ku and the time period Pu. So this thing Ku you can get it from you can use any stability analysis, so you can use Bode stability criteria and then find the value of the ultimate gain of the system. So right now it is around 1920, that is 720. You can try solving it on your own till 7:30, and I will discuss the solution at 7:30. Let me know if you have any doubts related to solving, and then we can do it. So in the question you have been asked to find Kc and tau I, that is you have to use these two correlations. So the first one is you have to find Ku and the second one is you have to find Pu, and then you can use this correlation. Pu is nothing but 2 pi upon omega C0, where omega C0 is the gain crossover frequency. So that thing you have to find using the Bode stability criterion. So once you have this omega C0, then you can also find the amplitude ratio, and from that you can just equate it to 1 and find the value of Kc, and that you can use over here to find the ultimate gain Ku. Sorry. So let's try solving this question. So yes, as discussed, we have to find these two parameters kc and tau I. So for that we need to find ku and pu. Ku is nothing but ultimate gain. So that you can find using the body stability criteria, and that body stability criteria states that at gain crossover frequency amplitude ratio is 1. So using these two information, you have to find this omega c0, that is gain crossover frequency, and then also you can equate amplitude ratio equal to 1 in order to find the value of kc. Kc, so basically that will be nothing but your ultimate gain. Now, while discussing what is body stability criteria, we mentioned that gain crossover frequency is the frequency at which the phase shift is minus 180 degree for the entire process. So over here, the process includes its first order term and the lag term. So corresponding to this first order term, the phase shift is nothing but minus of tan inverse omega, and corresponding to this lag, that is exponential term, it is nothing but minus of omega tau in, basically you have to convert it into degree. So how you do that is basically, so over here time constant is 1, and over here the dead time is minus 1.02. so it will nothing but tan inverse minus of omega tau. So tau is 1, so we just write it as omega, and then we have this tau d was 1.02 omega, and this you have to convert it into degrees, so it will become 180 upon pi. Now you can just simplify this term, and you can get an equation that is 180 degree is equal to tan inverse omega plus 58.45 omega. So this is the non-linear equation that you have to solve, which will give you the value of omega c0. So you can try using trial and error. So that is, just put the value of omega equal to 1 and then check whether the equation is being satisfied. Then put the value of omega equal to 2 and then check the equation is satisfied or not. You can use this approach, or you can also use this fixed point iteration. So that is basically, you can write omega as 180 degree. Just give me a minute. So you can just write it as 180 degree minus of tan inverse omega upon (58.45), and then you can start by again randomly putting the value of omega something over here, then you can get some value of omega, then again put it over here, and keep this iteration until the value of omega converges. So you can use any of the two approaches, whatever suits you. So once you do that, you can get the value of omega c0 as around 2. So once you have this value, you can calculate the amplitude ratio. So amplitude ratio is nothing but the product of the amplitudes of individual block. So for the first order term, that is kp upon tau s plus 1, it is usually kp upon under root of omega square tau square plus 1, and for this exponential lag, it is nothing but simply 1. So over here, there will be, so we have to find this kc. So the amplitude ratio will become kc upon under root of 1 plus omega square, and for this exponential lag, it is nothing but 1. So this kc we have to find, and at gain crossover frequency, the amplitude ratio is 1. So this kc will become under root of 1 plus 2 square, that is under root of 5. Under root of 5 will come around 2.24. So this is the value of Kc, or you can write it as Ku, ultimate gain. Since we had used this Bode stability criteria to find it, we can term it as ultimate gain. So once we have this Ku, you can just use the Zn table, that is the proportional controller gain, or the Kc will become 0.45 times of Ku, and tau I is Pu upon 1.2. So this will become 0.45 into 2.24. So this will come around 1.01, and Pu is nothing but time period, that is 2 pi f, or 2 pi upon omega c0 upon 1.2. So you can put the value of 2 over here and then solve it to get the value of tau I as 2.62 minutes. So these are two value of controller parameters. So we can just verify the value that we got over here, that is omega c0, as well as the amplitude ratio, from the Bode stability, from the Bode plot also. So I will just show you how you can quickly do it, that is quickly find the value of omega c0 and then ultimately the amplitude ratio by using the Bode plots. So for that I will show that to you in MATLAB. So first we'll just define our Laplace domain variable, that is Tf of S, that is the function that we will be writing will be in S domain. Then we need to write the equation corresponding to our system, that is what we were having was this term 1 upon s plus 1, then exponential of minus of 1.02s, that is 1 divided by s plus 1, and we were having exponential of minus of 1.02 into s. So this is our process transfer function for which we have to plot the Bode plot. So I think the command is simply Bode, and in order to plot the grid lines you can just write this. So over here you can see that we have this Bode plot. So that shows the relation between, so in the class we had discussed that this y-axis will be amplitude ratio, but usually amplitude ratio is also represented in terms of decibel. So decibel is nothing but 20 log times of the amplitude ratio, 20 log to the base 10 times of the amplitude ratio. So that is what is plotted over here, decibels versus omega. And similarly we have this phase diagram over here, and then I discussed that Bode criteria states that the gain crossover frequency is the one at which the phase is minus 180 degree. That is, if this is minus 180 degree, corresponding to that, whatever frequency that we are getting in this plot is omega c0, and at that frequency the amplitude ratio should be less than 1. So we can just find the value of frequency at minus 180 degree. So that I will just show it to you. We'll just zoom into this plot. So over here yes, so over here we can see that the So over here we can see that this is the line corresponding to minus 180 degree, and this intersects our Bode plot at this point. So we will just find what is the frequency at that point. So minus 180 degree. So corresponding to that, you can see that the frequency is mentioned over here, that is 2. So that is what we had find using the trial and error method also. So over here, the gain crossover frequency that we found out, that you can find it by using this trial and error, is 2. So that is the same thing that is obtained from the Bode plot. Over here you can see the frequency is 2. Now at this frequency of omega equal to 2, you have to find the amplitude ratio. So at this frequency you can see that the magnitude is minus of 6.98. So that is, in decibel, it is minus of 6.98. But we know that decibel is usually 20 times log 10 of amplitude ratio. So this is the formula that we know, but we have to find the amplitude ratio corresponding to that. That is, also you can see that at omega c is equal to the amplitude ratio, if we just project it on y-axis, so this will come around 6.98. so that is how we are getting this value 6.98. Now we have to convert this decibel into amplitude ratio. So you can just divide it by, so amplitude ratio will become 10 raised to this upon 20, that is minus of 6.98 divided by 20. So this will give us amplitude ratio. So the amplitude ratio comes around 0.447. Now you also know that the gain, ultimate gain, that is Ku, will be 1 upon amplitude ratio. So using this formula of the gain margin, we had this gain margin is equal to Kc upon amplitude ratio. So using that, yes, I think, yes, using that equation you can just find the amplitude ratio as 1 upon AR. So it will become 1 divided by AR. So it will come around 2.23 or 2.2336, that is ultimately 2.24. So that is what we had found the amplitude ratio from the formula also. So it is around 2.24. So using this value of Kc and omega c0, we just use this. We calculated the controller parameters. So what we can do is we can now use these controller parameters over here and then check the response of the system, and you can see that if we had used only the conventional PID, if you use this PID controller parameters, so the tuning becomes very easier and you can just check the control performance also. So the next question that we are solving is again similar to this question. So yes, in this question, the controller parameters that we found was 1.0 and 2.62. Now, in the earlier question, we didn't have this measurement term, that is the measurement term was straightforward one. Now in the next question, we have this lag in this measurement, that is exponential of minus s by 2, and for this given system, you have to again use this Zn tuning parameters to find the controller setting, that is the value of controller gain Kc. So in that question, in this question, you have been asked to design a specific controller. So you have to find the parameters related to Kc, tau, related to proportional controller, Pi controller, and PID controller. So again, you can use that table and try solving it. So you have to again use this table and solve the question. So right now it is around 1946. I will give you around 2 to 3 minutes. So you can just try solving this question and then I will just share the solution with you. This will be a fairly lengthy question. So you just figure out how will you move around this question. So again, just to repeat, so you can just simply plot the bode of this given system. So for that, you can use this transfer function that basically you can use this block e raised to minus of s by 2 upon s plus 1 to s plus 1. So corresponding to this function, you can plot the bode diagram, and from that you can calculate omega c0, and using that you can find the amplitude ratio kc, and then just take the inverse of this to find the value of ku. 1 upon amplitude ratio will give you, sorry, so this will give you omega c0, and 1 upon amplitude ratio will give you kcu. So using this to kcu, and then using this you can also calculate pu. Then we have to use this table in order to find the all the controller parameters. So we write this. So how do you get this equation? So basically, in absence of controller, the transfer function without the controller will be nothing but the product of the transfer functions block. So that is why we write this equation over here. So I'll just show you the solution using MATLAB. So first let me just write the transfer function. So sys2 is nothing but 1 upon s plus 1 into 2s plus 1, and then we have this measurement lag term exponential of minus of s by 2. We can also plot the response of this plot of the system and just check how does it behave. So if you provide the step input to this system, so you can see that corresponding to this measurement lag we can see a delay, then rest it will behave in such a manner. It will keep on increasing and then it will ultimately become constant to some next value. Now if we just plot the Bode plot of this term, so this is the Bode plot, and again to find the crossover frequency you can just find the frequency at minus 180 degree. So I will just zoom out this plot, and at minus 180 degree, that is at this line, wait a minute, let me just replot the diagram. And so this was the step input, not the earlier one that I showed. This is the step response. That is not no use for analyzing the stability. We have to plot the Bode plot. So this is the Bode plot corresponding to that. I'll just zooming it out to find the frequency at phase of minus 180 degree. So it is around this point, minus so minus 180 degree comes around this point, somewhere around 1.66. that is omega c0 is 1.66, and the corresponding to that at minus 1.66 the amplitude ratio comes around minus of 16.5. that is omega c0 comes around 1.66 and amplitude ratio comes around, not amplitude ratio, the decibels comes around this term minus of 16.5. so using this minus of 16.5 you can find the amplitude ratio as 0.1496 is the amplitude ratio. So KCU will become 1 upon 0.1496. So this will become 1 divided by 0.1496, around 6.68. That is, you can write it as 6.68. So you have this KU, and you can calculate PU as 2 pi upon omega C0, and that will come around 4, close to 4, and then you can use these two value in this table and find each of these parameters, proportional controller, PI parameters, and similarly parameters corresponding to this PID controller. So that is how you can find the tuned parameters of the PID controller using the Zn tuning method. So in this we had used the Zn tuning method. However, if this was the case of any other method, so corresponding to that also you have this table, and that tables you have to use basically. So this is just one approach that I showed to you. So now I think we can move on to the content of this week. So yes, as discussed, so we'll start with cascade control. So most of these are conceptual topics, whereby I will just demonstrate how we can use this in practical, how you can study this practical implementation of each of these controller. So there won't be many numericals related to this. They will be very simple numericals, whereby you have to find the process model or something similar to that. But the crux of these topics lies in the methodology in which we implement this controllers. That is, what all control loops that we are using, that we need to study basically. So yes, ultimately many of these techniques will use PID controller. So the main performance is that we are improving the performance of these feedback controllers by using some additional mechanisms. So we will start with this control of the furnace reactor by using, so I'll just demonstrate this cascade control, and then later on we will study different examples of this cascade control. Then we'll move on to split range control, and then different kind of selective controllers. So in that we will study this override control, and then we can discuss this auctioneering control. So let's start with cascade control. So this is just the motivating example, so that will help you understand what do we mean by cascade control. So over here I have given an example of a furnace whereby our main aim is to control our main aim is to heat this fluid, that is from cold oil to, we have to heat it till hot oil. That is where to increase the temperature of cold oil by some degrees. And how do we, and we use that by employing this furnace. So basically we will just burn this flue gas, so that will heat up this inlet oil to some desired temperature. So the controlled variable in this term is nothing but the outlet temperature of this hot oil. So that is the temperature of the hot oil, that is a controlled variable. And how can we do that? An obvious technique is to, so we are basically ultimately heating this oil by using this fuel gas that we are burning. So we can control the flow of this fuel gas in order to manipulate the temperatures, and or in order to control the outlet temperature of the oil. So that is the manipulated variable will become the fuel gas flow. So if we had to just write the transfer function of this system, we can just write output upon input. So that is basically temperature of the oil upon the flow rate of the fuel gas. So if we take a look on how this control method will work, is, let's say if we have the desired set point of YSP, and at a given time instant the temperature of the system is Tm. Now if I increase the set point to Tm plus, let's say 5, that is, I want to heat the oil by a higher degree. So let's say from 200 degree I have to heat it to 205 degree. So it is obvious that since I want to increase the temperature, the fuel gas flow rate should also increase. So in order to increase the fuel gas flow rate, what we will do is we will increase the valve opening. So once we increase the valve opening, you can see that the amount of gas passing through this valve will increase. So the flow rate will increase, and this gas will ultimately get burned in the presence of air, and combustion will take place. So the temperature of this furnace will increase, and then there will be heat exchange between furnace and this what pipe, whatever we are using as the vessel, and then ultimately the temperature of the hot oil will increase. So once the temperature of hot oil has reached the desired set point, again the control valve will act and try to regulate or decrease the fuel gas flow rate. So this is the steps that will be taken by the process in order to control or reach the desired set point of this hot oil. So that is achieved using this conventional control diagram. So over here you can see that when we are controlling the temperature by manipulating this valve, we are just simply manipulating the opening, and by manipulating the opening, ultimately we are controlling the fuel that goes into the system. So we are not directly monitoring the flow rate, that is, we are not measuring the flow rate. What we are doing is we are just changing this valve opening, and then on the basis of this temperature we can increase or decrease. So we are not monitoring the flow rate. That is the crux over here. So what might happen is, let's say the fuel gas will come from a particular pipeline. So there will be some overhead tank over here, there will be some valve over here. Now if on the what you can say, if on the upstream there are these pressure changes due to which the fuel gas flow rate might increase, so that is, there are disturbances in the system due to which the pressure of the system increase, then the fuel gas, then what will happen, the fuel gas flow rate through this system will increase, and then again the fuel gas flow rate increases, so the temperature, so the fuel gas will get burned, the temperature of the furnace will rise, the heat exchange will take place, and then ultimately this hot oil temperature will increase. So you can see that once the disturbance occurs, fuel gas flow will increase, it will get burned, furnace temperature will increase, and then ultimately once the temperature of oil increases, then only the system will regulate the fuel gas flow rate. That is, the system won't be able to react very fast to this disturbance. So if in terms of diagram, if I had to show it to you, so just consider a response to a disturbance in the fuel gas header of the PSIG1G. That is, if the pressure increases by let's say 1 pound per square inch, then you can see the fuel gas flow rate will increase. So that is what this diagram shows over here. So initially the fuel gas flow rate is increasing due to this disturbance. So let's say the response over here, you can see that the temperature of the system will remain at steady state till 1 minute, and the effect of this increase in the fuel gas flow rate will be felt only after 1 minute. So after the effect is felt due to this increase in the flow rate, the temperature will increase, and once the temperature starts increasing, the flow will be regulated such that it has to maintain this temperature set point. So after the effect is felt on this temperature, then only the flow rate will start to regulate itself. That is, we can see that until 1 minute there is no effect on the outlet temperature, so no control action takes place. So what will happen by this by this 1 minute, the temperature of the system won't be affected and it will start to rise. So in case of critical process, this can be a very crucial factor. That is, because of this dead time of 1 minute, the controller did not take any action for 1 minute. That is, the fuel was, so a large amount of fuel had passed, so a substantial amount of extra fuel went into the system, which caused the temperature to rise to a very high value. So in order to develop an optimal control, so we need to limit the effect of the disturbance only to valve. So that is, if the pressure increases or if there are any disturbances that increases, so the flow rate should still remain constant unless we are manually changing it, that is we have increased the set point. So the flow rate should remain constant. So how can we just manipulate the, how can we limit the effect of the disturbance up to the valve? So that, for that, what we need to do is we need to use an additional control loop, so that we will study in this cascade control. So yes, so over here what we are doing is we are using this additional control loop, whereby we will measure the pressure after the valve, such that if there is any disturbance in this system, the pressure will increase, and then we will have the pressure transmitter that will monitor the pressure. And once we see any changes in the pressure, then as soon as we see the changes in pressure, we can manipulate this control valve in order to fix this value of pressure, or ultimately the flow, to some fixed value, that is over here. Let's say if the set point is 600, so that we need to fix. So in the earlier case, we weren't considering the disturbances. That is, here we weren't considering the disturbances in conventional controller, but there will be additional disturbances such as this cold oil temperature. So this oil temperature can also fluctuate. This supply pressure of fuel gas can also fluctuate. So we need to account for all of these disturbances, and we do that using cascade controller. So what the system will do is, so given the changes in this hot oil temperature or the set point, the temperature controller will provide a set point to this pressure controller. So corresponding to, let's say if we are having a rise of 10 degrees Celsius, then it will say that in order to increase the temperature by 10 degrees Celsius, you need to increase the flow rate by, let's say 20 meter cube. So corresponding to that, the set point of the pressure controller will increase, and it will, let's say, change by 100, and it will become 700. So since this set point of this system is changing, this control valve will open in order to increase the pressure to 700. So earlier it was 600, so this control valve will open in order to regulate the pressure from 600 to 700. So we are having a precise control on the amount of fuel that is going inside by what controlling the pressure of this system. So over here, that is why we are using, so this loop is called a secondary loop, which is basically used to control the flow of the fuel gas given this set point. So yes, in cascade control you can see that we are having two loops in order to control a single output. So that is, we are controlling the temperature of the system by using two control loops, by also monitoring the pressure as well as the temperature. The control variable in this term will become temperature as well as the flow rate. So this flow rate we are monitoring in order to negate the effect of the disturbance, and this is our main purpose. So this is the brief of the cascade control. So I will summarize it. So the temperature control will have its own set point. So yes, that is, if earlier the oil was at 200 degrees Celsius, I can give a new set point as 210 degrees Celsius. So it will have its own set point, and the output of this controller, so corresponding to this 10 degrees Celsius rise, there will be a temperature controller which will give an input to the subsequent secondary loop, that can be a flow controller, pressure controller. So the output of this will act as an input or the set point of the flow controller. That is, temperature controller is going to tell me for a particular requirement of set point temperature and current temperature what should be my flow of the fuel going into this furnace. So this will act as a set point for this flow controller, which is going to manipulate the valve opening. So over here, yes, we are having two control variables, and both of these control variables are connected through a single manipulated variable, that is the valve opening, such that the output of one acts as a set point for another. So these two are cascaded together, so that is why we call it as cascade control strategy. So yes, from the earlier plot, you can see that from the earlier control strategy, as soon as we were utilizing a step change, the temperature was kept on rising, and then it became constant. Now, if you use this cascade controller, then from the plot you can see that a perfect control is obtained after a few amount of time. So even though there is disturbance in the gas header pressure of 1 psig, the flow will increase, and the secondary loop will try to regulate the pressure, so not much effect will be felt on this outlet temperature. That is, we are having a proactive response by using a cascade control. So over here I have just shown a block diagram corresponding to cascade control system. So as shown in the earlier diagram, we had these two loops, that is, this one is the primary loop and this one is the secondary loop. So corresponding to that system, you can see that this is the secondary controller that will control the parameters of the secondary control loop, that is the flow or the pressure. So that will basically give the set point to this control valve GV, and then there will be this primary controller that in our case was this temperature controller, and the secondary controller was this flow controller or the pressure controller. So usually the response of this secondary controller should be fast, and ultimately, since we are manipulating the flow or the pressure, so these are the processes with fast dynamics. So since the processes are with fast dynamics, if we use this PI controller, then there can be a delay in the process, that is, it will take some time to implement the control action. That is why we usually use this P controller in the secondary controller. So yes, we have this secondary loop, and then ultimately we have this primary loop that will use this primary controller to control the temperature. So there is this additional example that you can take a look on. So this is an example of jacketed kettle, whereby you use this cascade control in order to regulate the temperature of the given system. So over here, let's say I'm having a feed of water, and I want to regulate the temperature, that is change the temperature of the given system having water by using a jacketed kettle, which is having the hot oil as the heating or you can say cooling medium. So what we do is we can change the flow rate of this hot oil, which has this temperature Ts. So if the flow rate of this hot oil increases, so the heat within the system will increase. So basically heat within the jacket will increase, and corresponding to that the temperature of the water will increase. Now it might happen that there will be disturbances in the system, that is the pressure of the hot oil or the fluid of the hot oil or the temperature of the hot oil can abruptly change. So what we do is we use this secondary controller or the secondary loop over here. So it will monitor the pressure or the flow rate. So once the flow rate of this hot oil increases, the jacket temperature will change. So we will monitor the jacket temperature in the secondary loop. So once we see that the jacket temperature has changed, then and it deviates from the set point, we can just change this valve opening. That is basically, we can change this valve opening in order to keep this jacket temperature fixed. So this is the purpose of this secondary controller. And then yes, we have this primary controller, whereby if we change the set point of this system, that is if we want to increase the temperature of the fluid or water from 80 to 90, so it will give the set point to the secondary controller in order to increase the jacket temperature by opening this control valve that increases or decreases the flow of the hot oil. Yes, this jacketed kettle example shows this cascade control strategy also. So this is the block diagram corresponding to this jacketed kettle. So you can take a look onto this. So these are few of the comments related to the applicability or the design of cascade controller. So as discussed, the secondary loop should be faster. That is, the cascade control strategy is effective if the secondary loop is faster compared to the primary loop. And most commonly, the secondary loop is flow control, which is typically fast and rejects disturbances in upstream and downstream pressure. So secondary loop should be tuned before the primary loop. That is, the parameters of the secondary controller should be tuned properly, and then only we can tune the primary loop. So primary loop should be tuned with a well-tuned closed secondary loop. That is what these 2 points are more or less similar. And if the secondary loop has a significant dead time, the cascade strategy will not be effective. So yes, if the process is itself very slow, then cascade control strategy won't be effective. That is, if the secondary loop is very slow, that is, if I just change the valve opening and the fuel gas or the flow rate through the valve increases, but it takes large amount of time in order to increase the temperature. That is, let's say in case of this jacketed kettle, if increasing the flow, if increasing the valve opening takes large amount of time to increase this jacketed temperature, then in such scenario, this secondary control loop is, we can say that it takes a large amount of time, and then cascade control strategy won't be effective, because more amount of fuel is going, still we are not seeing any effect on this TJ. Yes. So we can take a look on this numerical in next class. So now, so this is the basic about this cascade control strategy that I showed it to you using 2 examples. So one was of the jacketed kettle example, then the other was using this furnace heater. Now we will quickly go on through this different other control strategies. So the first one amongst them is the split range control. So in the earlier case, if you remember that we were having one controlled variable, that is the temperature of the hot oil, and we were controlling them using 2 different control loops. Whereas in case of the split range control, we can have several manipulated variables that are used to control single controlled variable. That is, there will be manipulated variable 1, manipulated variable 2, manipulated variable 3, and all these are used to control a single controlled variable that can be, let's say, temperature. So such kind of process, you can see that the adjustment of both inflow and outflow from a chemical reactor in order to control the reactor pressure. That is 1 output and 2 inputs, but they are not simultaneously working. That is, if we take an example of this reactor whereby we have to control this pressure. So we can control the pressure of the system by opening this inlet valve. The pressure will increase. Similarly, we can control the pressure of the system also by opening this outlet valve. So if you open the outlet valve, the pressure will decrease, and if you open this, the pressure will increase. That is, basically we can control the pressure by using either of this. That is, we are having two manipulator variables just to control this pressure. So in that we can use the split range control. So this is one example. Similarly, the use of both acid and base to control the pH in wastewater treatment. So we can either add acid or we can either add base in order to control the pH. So this is the second example. And another example is in reactor control, where both heating and cooling medium are used to maintain the precise regulation of reactor temperature. So let's say if we have a reactor, we can have a jacket. And in that we can have cooling water inlet as well as cooling water outlet. Similarly, we can have this steam inlet also. So yes, this heating medium of steam, and then let's say we can have some drain valve over here in order to remove the condensate. So yes, we can use this cooling water as well as steam in order to control the temperature of the reactor. So this is another example of the split range control. So let's take this example of the gas phase reactor, whereby we have to control the pressure of the surge tank. So let's just consider gas phase reactor, whereby we have this outlet valve. And then we have this inlet valve over here, and we have to monitor the pressure of the given system. And the controlled variable is pressure. Now let's say if the pressure of the system increases, let's say if the pressure was earlier 100 psig and it increases to 200 psig. So, and this inlet flow rate is constant. So the valve opening is, let's say, 100% open. And similarly, the outlet valve is also 100% open. Let's just consider this scenario. Now, if the pressure of this system increases and we have to maintain this set point 200 psi, that is, it was at 100 psi, and due to some disturbances this pressure increases to 200 psi, and we have to decrease the pressure. Since it has increased from 100 to 200, we have to again decrease the pressure from 200 to 100. So we can try to achieve that by opening the outlet valve. So let's say if the outlet valve was earlier closed, okay, then in order to decrease the pressure, what we can do is, over here I'm just plotting the valve opening. So earlier it was closed, that is 0 corresponding to close. Then since the pressure is increasing, I will give the controller input in order to increase the valve opening to 100%. Okay, so over here it becomes 100% open. Now what I observed was, even if I increase the valve opening to 100 psi, the pressure has not decreased and it has decreased to 150 psi. however, we want it to be decreased to 100 psi. So even if I have increased this valve opening to 100%, the pressure within the system has only reached 150. That is, I have increased the valve from 0 to 100%, and then my manipulated variable, in this case the outlet valve or the outlet flow rate, becomes saturated. That is, I can't further increase the valve opening. So that is what we call it by saturation of the manipulated variable. So I don't have controllability over this. So now what I can do is I can try to manipulate the inlet flow rate. So earlier the flow rate was open 100%. So over here, let's just call it as outlet valve. So this was the plot for outlet valve. Now the inlet valve was 100% open at earlier. So once this, we can see that the MV1, MV2, that is the outlet valve, has reached saturation. At that point, we can start closing the inlet valve in order to regulate the pressure. That is, we can start decreasing the opening, that is closing the valve again to 0. We can close the valve as per our required pressure. So we observe that at closing the 100% valve, the pressure reaches the desired set point of 100. Yes. So such a kind of controller whereby we use both of this manipulated variable in order to control this single controlled variable, we call it a split range control. So over here, so this diagram, you can see that this will be my controller input, the controller output. So usually it will be controller input, we give it in 4 to 20 milliampere. So this is 4 milliampere, and that 20 milliampere. So this is basically the final range, maximum range of the controller input. So how can we use this? How can we decide how should we split this automatically? That is, the controller will give the signal to the manipulator input, basically in terms of the current signal. So we know that the current in terms of controller is simply 4 to 20 milliampere. So that is, when I say the current is 4 milliampere, it says that the valve should be at the 0 state, that is, the valve should be closed. Similarly, when I say 20 milliampere, that means this original valve should be at 100% open state, that it should be in another extreme state. That is, if I take this outlet valve at 4 milliampere, it should be closed, and at 20 milliampere it should be open. Similarly, for this valve, we can see that 20 milliampere it should be closed, and at 4 milliampere it should be 100% open. So in order to obtain a split between these two valves, we can come to a midpoint over here. So 4 plus, so the range that we are having is 20 minus 4, that is 16. So we can just divide it by 2, so it will become 8. So 4 plus 8, that is 12. So until this 12 milliampere, we can generate the split such that until this 12 milliampere, the control valve reaches the 100%, the outlet valve reaches 100% opening, and beyond this 12 milliampere, the valve will become saturated, and then the inlet flow rate, in this case this flow rate, will be manipulated by closing the valve. So this is how we obtain this split amongst this among these two manipulated variables. So that is what I have explained over here. So this is another example of split range control, whereby we are controlling the reactor temperature by manipulating the steam flow rate as well as, I think, cooling water flow rate over here. So it is not, so yes, we can also develop a design whereby there is a fair amount of overlap between these two actions. That is, over here we can see that there is no overlap between this of this. So once this valve has become 100% open, then only the second valve will take any action. Whereby we can also make this overlapping action as shown in this diagram, that is at 10 milliampere. Even though the product valve keeps on opening at 10 milliampere in this diagram, the vent valve will also keep on increasing. And at 14 milliampere, the product valve will get closed and the vent valve will again keep on increasing. So this was the example that was already discussed in the class, which showed that how you can design a system whereby there is a fair amount of overlap between these two control actions. So if you have any doubt related to the cascade controller as well as the split range control that we discussed, you can ask, or else we can move on to the override control. So yes, let's take a look on this selective control or the override control. So in split range control, we see that we had multiple manipulated variable in order to control a single controlled variable. Whereas in case of selective control, we have the reverse of that. That is, we have more controlled variable than the manipulated inputs. So if in the sense that, let's say we want to control temperature also, pressure also, temperature at some fixed point, let's say temperature of the distillate, temperature of the bottom, but we only have this feed input as the manipulated input, then we can say that we have more controlled variables than the manipulated input. So in such a scenario, what we need to do is we need to select which out of the given multiple inputs, let's say if out of the given five output that we want to control, which one is the most critical to us. So if we take an example of polymerization reaction, then we need to control the temperature such that the reaction does not go into a runaway reaction, or else there can be a major accident. So this temperature control in case of polymerization reactor can be a critical control that we want to achieve. So from the given set of controlled variables, we need to identify whichever controller is critical to you, and then we will manipulate it using the manipulated variable. So we won't be manipulating the other variables first. We will be just controlling the most critical parameters first by using the manipulated variable. And when the other controlled variable becomes critical, then we can shift the control from one variable to the another. That is, after we have achieved this temperature to a desired set point, then we can look on to the next hierarchy, we can look at the next critical variable, and then we can try to control that. So this is what we mean by selective control. That is, we are selecting which control which control variable we want to ultimately control. Now let's take a look on the example for this. So over here we are having a distillate, let's just consider a level control of a tank, whereby we are controlling the level by using this pump. Basically we are controlling the output flow rate. So we are having a flow controller, that is, we will be having a level controller that will not do nothing but manipulate the flow rate over here, flow rate of this. So in order to manipulate the flow rate, rather than we are just passing this input to a controller that will control the speed of this pump. So based on this level, we are controlling the speed of the pump. That is, the speed of the pump should be manipulated by the level. So what might happen is, let's say the level decreases to some extent. Okay, so the level comes over here, so the flow through this pump will also decrease. So we are measuring this flow, and flow decreases beyond this critical value of flow rate. So if you are using a pump, you would have known this problem of cavitation, whereby if the flow rate is very low, then there will be this this vapor. So there will be this vapor generation in the pump that will lead to the cavitation, and that will lead to the corrosion, and it will ultimately damage the pump. So you need to maintain a minimum flow rate through this pump. So in order to do that, what we will do is we will use this selective control, or this override controller, whereby once this level of the tank has gone beyond a certain amount of level. So if, let's say, if the level decreases by 10%, then we can control the flow rate outside by changing the speed of the pump. Or alternatively, what you can do is you can just manipulate the flow rate also. So if the flow rate is less than 20 meter cube per hour, then you can again decrease the speed of the pump, so that less amount of less amount of water flows through this pump, and basically the level decrease is controlled, and the cavitation doesn't occur. So that is what I mean to say is, if the level is above 10%, or if the flow rate is above 20 meter cube, then in order to control the level, we can control the level of the tank by increasing the variables, by increasing the input to the speed pump, that is by increasing the speed of the pump. And once it reaches beyond this 10%, or the flow decreases, then what we will do is we will switch off this control. That is, at that point we won't be controlling the level of the tank. What we will do is we will be controlling the flow rate of the tank. So in order to control the flow rate, we will just decrease the pump. That is, we are overriding this level control in order to control the flow rate through the pump. So that is where we use this term override control. And then in the class we had discussed this another example of the level temperature override, whereby we had to control the level of the distillate tank by manipulating the outlet flow rate. And once we increase the outlet flow rate, we can see that even if this outlet flow rate has been increased or it has been decreased, due to this presence of this steam valve, the composition will keep on changing, or that is the vapors might keep on increasing. So once this level has decreased by some amount, we take into this steam control valve into account. So this was the example discussed in the class. It was also related to this split range control. So in this case, it is the level temperature override. So the level keeps on falling because we are vaporizing more amount of liquid, and in such a case we are having a level controller. In this case it is an outlet valve. So the maximum we can do is we can close this valve if the level keeps on decreasing. That is, if level keeps on decreasing, we can close this valve 1. So what we can observe that even when the valve has been closed 100%, the heating in this reboiler section will keep on increasing, due to which the level will keep on again significantly decreasing due to this presence of this steam that we are providing. That is, in such a case, when we have secondary level controller, which will have the set point which is given by this critical level value, and only when this level decreases beyond this critical value, this controller value will give a control input to this to lower the steam flow rate. And then because of this low selector switch, we manipulate this control valve to this steam. So once this level has gone beyond some critical value, gone beyond this critical value, we will start to manipulate this steam flow rate. So that is what we mean by this low level switch. That is, if we want to keep some quantity level of flow above certain amount of above certain critical limit, then we use this low selection switch. Similarly, we are having this high selection switch, whereby if we had to maintain the flow rate above this 500 meter cube per hour, let's say for example, then we use this high selection switch. Then another kind of control strategy that we are discussing right now is auctioneering control. After that, we will discuss ratio control, inferential control, and then we will end today's lecture. And in the next class, we will start with model based control. So in selective control, we first studied this override control. And next, what we are going to study is auctioneering control. So this is another type of control which is a part of selective control, whereby we are having multiple measurements. So let's just consider an example of distributed parameter system given by a fixed bed reactor. Distributed parameter system, whereby we want to monitor the temperature within this fixed bed. So what we can do is We can have a temperature sensor over here T1, temperature sensor over here T2, temperature sensor over here T3, temperature sensor over here T4. That is, we are having many measurements. So over here we are having 4 measurements, and if we only have the single manipulated variable, that is if we consider the feed fluid as the input, then we are having a single manipulated variable feed fluid, and then we have these 4 measurements. So out of these 4 measurements, which measurements should we use in order to control the process? That is what we will do by auctioneering control. In override also we were having many measurements, but for those individual measurements they had their own control loop, as well as one of the control loop was active at any time, which was used to move the manipulated variable. That is, at a time only one control loop was active in case of this in case of the split range control. So yes, over here you can see that this is one control loop, then this is another control loop. So there are this different control loop for multiple measurements. So in this case you can see that level transmitter was a measurement, this flow transmitter was a measurement. So we were having multiple measurements, and we were having only this manipulated variable of pump. However, these multiple measurements were having their individual control loop, whereas in case of auctioneering control, they will be controlled by a single, most probably controlled by a single control loop. So yes, as discussed, so we can have multiple measurements. So in case of fixed bed reactor, what we want to do is we want to control the maximum temperature that is observed in this reactor, so that it doesn't deteriorate the catalyst performance. So catalyst will get deactivated or charring, or some kind of process might take place in catalyst. That is basically it can get deactivated at high temperatures. So we want to control the highest possible temperature within the fixed bed reactor. So what we will do is, we will, out of the given measurements, we will keep on monitoring where which of the sensors give me the maximum temperature, and we will try to control that temperature only. So that is, of the given n measurements, we will find out whatever the maximum measurement is, and it will give us the idea of hotspot that will give us an that will be used as a controlled variable. So this is an example of an auctioneering control, whereby we are, of the given measurements, we are taking an auction to find which of the given measurements give us the maximum temperature, and then we are controlling that. Now the next control strategy is the ratio control. So in chemical industry, an important control problem is to combine 2 or more streams in some fixed ratio. That is, examples of this include blending of reactants entering a chemical reactor, or injection of the fuel air mixture. So in case of this reactor, you can take this Haber-Bosch process for the production of ammonia, whereby we want to control the ratio of nitrogen to hydrogen in 1:3. So we want to control this ratio. So in such process, we can use this ratio control. So let's say if this was the flow rate of nitrogen, and this is the flow rate of hydrogen, and then this diagram demonstrates how we can use the ratio control to maintain this ratio N2 to H2 as 1/3. So this is the nitrogen. So we will monitor the flow rate of nitrogen using the flow measuring element. Then we are having this set point block over here, whereby we will give the set point, that is the ratio as set point, that is 1/3. So corresponding to this ratio 1/3, if the flow rate was, let's say, if the flow rate is QA, then this controller will give the set point to this control valve, that is the flow rate of the hydrogen should be 3 times of QA. Okay, and this flow rate we are getting by this flow measuring element. So the flow rate of the hydrogen will be obtained by this flow measuring element. So this controller will get this flow of this hydrogen, as well as it will get the set point. So the set point, that is basically how much should the flow rate of hydrogen should be. So in this case it should be 3 times of QA. So this set point will be given to this controller. Based on that, it will take the controlled action, that is increase the valve opening to increase the flow rate of the hydrogen. So that is how it will control the ratio of nitrogen to hydrogen. So corresponding to this system, we have the simple block diagram of this ratio controller. So the set point of the system will be nothing but Gm times Kr upon Qa, where Kr is the ratio, Qa is the flow rate of the fluid A. So this will give us this set point to the ultimate to control the flow rate of the B. So we are only controlling the flow rate of the hydrogen. So we are monitoring the flow rate of nitrogen, and then we are using this control loop in order to control the hydrogen to maintain this fixed ratio of 1:3. So over here, this is a commercial furnace air to fuel case study, whereby the furnace burns the natural gas in order to heat the process liquid. So we are having this fuel, which is natural gas, then we are having air that is necessary for combustion. So these two, fuel and air, are then combusted in order to heat the process liquid, and then the processed variable in this case will be the temperature of the processed fluid as it exceeds the temperature. And our aim is to maintain this ratio of air to fuel, that is the ratio of air should be 12 times the flow rate of the fuel. So in order to maintain this liquid temperature outside, so liquid temperature outside of the furnace. So what we will do is we will provide the set point of 12 is to 1 to this ratio controller, and then the process will keep on occurring. And then there are this other control loop also in this furnace air to fuel ratio case study, that is to maintain the liquid temperature, the controller will adjust the flow rate of the air as well as fuel using the ratio control strategy, and the flow rate of the process liquid can act as a disturbance to the process. That is, if this disturbance increases, okay, then there will be the rise in the temperature or decrease in the temperature. Then corresponding to that, we will measure the temperature, and then we need to increase the fuel to air ratio also. That is whereby we will increase this air ratio, and corresponding to the ratio, the fuel flow rate will also increase in order to compensate for this disturbance. This is an example of a ratio controller whereby we are neglecting the disturbance also. So ratio controller just doesn't necessarily mean it doesn't only have this purpose that we just need to maintain this ratio control to some fixed flow rate. Even if there is some disturbance, then the flow rate of the combined stream should increase in such a manner such that this ratio is maintained. Now the last control strategy that we are going to discuss today is this inferential control. So this we had also discussed in the earlier classes. So in some for some control variable, we can't conveniently measure them. Such as an example, the composition may require large amount of time to be analyzed. So we can't use this composition control directly. So if we want to control the composition of the outlet stream, we can't directly monitor the composition. So in order to control such a system, what we use is an inferential control. So we know that the composition of the product might be affected by temperature and pressure. So if temperature and pressure changes, then the composition of the product will keep on changing. So in scenarios whereby the measurement of composition might not be that frequent, what we use is this inferential control, whereby we measure secondary measurements, that is temperature and pressures, and then using the secondary parameters temperature and pressure, we have this mathematical model using which we can infer the composition of the product. That is, we can pass the inputs temperature and pressure to this mathematical model, and then we can get this composition of the product. So such kind of sensors or the measurements are known as this soft sensor. So we use this soft sensor in order to obtain the composition given the temperature and pressure of the system. So this temperature and pressure can be measured easily. So once we have these measurements, we use this mathematical model to estimate the composition, and then based on the deviation of the composition, we can take the control action. So over here we are having a block diagram of an inferential control. So the ultimate output of this, so this is the process, and the ultimate output we can call it as composition. But we can also measure the temperature and pressure of the process. So these are fast sampling, so temperature and pressure can be measured instantaneously, whereas this composition can be measured by via slow sampling. So it might take hours, whereas this will take just a matter of seconds. So we will be having this loop whereby we will be using this fast sampling to measure temperature and pressure, and then on the basis of this input and then mathematical model, that is basically inferential model, we will find the composition of the system, and then that composition of the system will be compared with the set point, and then the control action will be taken using this secondary measurement. So yes, the key features of this inferential control are that indirect control of the desired variable through a regulation of a conveniently measured secondary variable. So the desired variable in our case was composition, and the secondary variable could be temperature and pressure. So the choice of this secondary variable depends on a few factors, such that it should strongly respond to variations in the desired variable. That is, if the composition changes, that should necessarily mean that the temperature and the pressure should also have been changed, and then we need to rapid and easy measurement of this temperature and pressure should be possible, and they should have preferably one-to-one relation with the desired variable. When we say one-to-one, that is corresponding to some fixed value of temperature and pressure, there should be only a single value of composition. Similarly, for a single value composition, there should be only one corresponding temperature and pressure. Then ultimately the desired variable can be inferred from the measurement of the secondary variable, and this process we call it as soft sensing, and then this soft sensor can be used to control the process. So yes, that was all for today's class. So in today's class we covered until these 3 topics, and then in the next class we will start with this model based controls.